rather than.
Is it this?
Yes. So today we have the presentations from the students on journal articles. So today, Hongqi, Hongqi's going to present to us a subsection, I guess a few sections of this monster long survey article. It's part focused on some non-dimensional numbers and some other basics of heat transfer.
Yeah, I'm Hongqi Guo. I'm just going to introduce the this journal paper, Additive Manufacturing of Metallic Components, Process Structure and Properties. It's a very new paper. It's actually published this October last year. And one of the authors is actually from the Ohio State University, Zhang from Department of Material Science and Engineering. So this, as Professor said, this is a very long paper. It's actually more than 100 pages. So I'm just going to introduce the first, I think it's 2 sections of this paper. So these are the contents. I'll first introduce the processes briefly, and then the feedstock materials and how the materials are manufactured. Also, there's some modeling, including the heat source, the temperature and velocity distributions, the cooling rates, and there are also some introduction of the non-dimensional numbers and the process stability. The first thing, the typical manufacturing process for alloys. These are our schematics of 6 processes. ABC are all directed energy deposition with laser, with electron beam, and with gas metal arc. D is the powder bed fusion with laser. Then we have ultrasonic additive manufacturing and binder jet process. In this paper, they just focused on directed energy deposition and powder bed fusion because they actually share similar fundamentals like high energy density heat sources, localized melting and solidification. For UAM and binder jet process, I'm not quite familiar with binder jet process, but I use the UAM machine like 1 or 2 days per week, so I can say it's definitely a totally different story because it's a solid state welding, no melting, no solidification like that. There's another thing that the authors mentioned in the paper, that these 6 manufacturing process can actually be divided into 2 categories. One is a direct process, and another one is indirect process. The direct process means the components can actually be obtained just from a computer model. So we don't have to machine it afterwards. We can just produce a net-shaped part directly from the model. And for the directed energy deposition and powder bed fusion are both direct metal processes, and UAM and binder jet are indirect processes. They require a intermediate process like casting, bulk sintering, and machining. So let's just focus on the BD and powder bed fusion. 2 technologies. You can see the there are two kinds of materials in the directed energy deposition, powder and wire, but for powder bed fusion, definitely it's just used powder. Then one interesting difference is that you can notice when we have powder as the feedstock, the production time will be high, and the dimensional accuracy will be high also. But the process with powder is slow and expensive. But when we have wire as feedstock, it's fast, cheap, but the dimensional accuracy is lower, and the surface finish is actually poor. Another thing is, as for the post process, you see some of the DED with laser and powder bed fusion requires HEAP, which is hot isostatic pressure. It's a typical process to solidify the metal components to reduce the porosity. You just put a component into some special furnace, which will give it a elevated temperature and also isostatic pressure.
Who's heard of it before?
Yeah, I think Tyler from our lab has used some HIP, right, with the UAM components. Yeah. Then, as I mentioned, there are some differences between the process with different feedstock materials, powders or wires or sheets. This feedstock materials actually significantly influence the quality of the additive the manufactured parts. So there's one question here. The paper says the typical particle size for powder bed fusion with laser in the range of 10 to 70 to 60 microns, but the powder for the PBF with electron beam is larger in size. I'm not quite clear why. Anyone has an idea? Just why the particles for the PBF with electron beam are higher than the PBF with laser.
Maybe it's because the heat transfer coefficients of the particle size is that why, because they're two different sources to like apply energy.
So I would say that this hasn't been clearly communicated to me either. I don't research E-beam, so I haven't really studied too much of it. The best of my understanding is that the E-beam process generates a considerable amount of electrostatic basically charge on the surface. And so when you get to too small particle sizes, the electrostatic charge causes repulsion problems. So part of what they do in E-beam is they actually heat everything up to slightly sintered, or create basically they turn what is powder into now very loosely connected powder. And my impression is that if the particles are too small, it's going to transition from powder into a fused block too quickly. So they have to go slightly larger. That's my understanding of it. But the heat source is very different. So.
Yeah. Okay. Then there are 4 typical manufacturing processes of the alloy powder: gas atomization, rotary atomization, water atomization. They are just simple, you can tell from its name. There's a video showing the atomization process.
I feel video larger.
Oh, sure. Well, it's not going to do it. I think it's fine. Yeah, you basically just melt the metal, then use gas or rotary disc or water to atomize the alloy. You get particles. It's pretty straightforward.
So they atomize it and then it cools as it goes down the channel, right? To solidify
And the plasma rotating electrode process. We use an electrode arc or plasma to melt one end of the metal bar, and the metal bar is actually rotating about its longitudinal axis. So the molten metal is ejected from that bar. Here's a schematic. You see a plasma is hitting the bar. Then it's also rotating with the motor. Yeah, and here are the SEM images of these particles. You can see the plasma rotating electrode process, should I call it PREP or PREP, generates the particles with a perfectly spherical shape and smooth surface. All these are the three simple atomizations generates powders not as good quality. For example, the gas atomization generates powders with deeper surface, and there are some small particles as satellites, which also increase the actually cores in the surface. Then the rotary atomization, the powder of that has smooth surface, but it's not spherical. It's kind of elongated. Then the water atomization is the one with irregular shape and coarse surface. Actually, because of this coarse surface, the components made by the water atomization powders actually has high surface roughness. So the quality of the powders actually significantly affect the quality of the components. The powder with a uniform size distribution will generate homogeneous melting and good interlayer bonding, and we can get a component with higher quality and better surface finish. For example, the PREP is the one with most uniform size distribution, and you can see from the optical image, the parts has very low porosity, but with water atomization, which has the least uniform size distribution, parts often contain gas bubbles and lead to porosity in the component. But even we know PREP is like the best method, but it's very expensive. So if you want to make a component, you might want to consider both the cost and the quality, definitely. I think there was one question on Tuesday about if the powders can be reused. In this paper, it says it can be reused, but the reused particles will have irregular shape and poor surface finish of the front. So that will definitely affect the final parts. Another typical feedstock material is alloy wires. It's typically manufactured by wire drawing, and it's relatively inexpensive than powders. But the wires with very small diameter is difficult to straighten and feed. So typically we use a larger diameter than 0.8 millimeter, which makes the melt pore size larger and will result in a rougher surface finish. But with alloy wires, there are some advantages like greater rate of deposition, and since it has much less surface area than powders, it's less likely to oxidize or absorb moisture or contaminants. These are the introduction of feedstock and process. Then there is also a lot of modeling work. First thing, a equation of the powder density of the heat source is given in this paper, which generates a axis-symmetric Gaussian profiles. The F here is the distribution factor. From the plot, we can see when F increases, the power is actually more focused. And there's for the previous question why the particles were or EB is larger than laser, I assume there might be some connection between that and this energy distribution thing, because laser can be focused to a spot radius on 50 micron, and for electron beam it can just be focused to 100 micron. Probably is one reason. And for the electric arc, the focus spot size varies in the range of a few millimeters, which is definitely higher than the laser or electron beam. Larger, I should say. Then, when we go to specific process for direct energy deposition, there is a process where the powder fly from the nozzle to the component to the build, so that will cause a heat loss during this flight. So a term involving this is added in the red box. The heat absorbed by the particles actually depend on the characteristic of both the particles and the heat source. As for the absorption coefficient of the deposit, it actually depends on the status of the deposits. Like this will, sorry. Yeah. This value is high initially when the feedstock material is not completely melted. Then it will reduce when the surface is melted. As for the powder bed fusion process, there is no flight process, so all the heat source energy just incident on the powder bed. And when the heat source incident on the powder bed, part of the energy is absorbed by the particles, and the rest of it just reflects. So the fraction of the heat absorbed by the particles depends on the particle size, packing density, and material properties.
So if you go back a slide, I may get this, sorry, I wanted the light point to the bottom, but I may get this to this today. I mean, what the schematic on the bottom right is showing is basically laser coming into the powder bed, and then there's all these internal reflections that happen. And so some of the, in terms of light bouncing off particle, and some of the light energy is absorbed by that particle, and some of it comes off. And you can imagine, too, that you get a pretty significant amount of the light that's actually reflected in the back end of the chamber. So it would be essentially energy lost in the chamber. So if you have a 100-watt laser, you're not getting 100 watts put into your powder bed. You're getting lots of that.
So to get a transient temperature and velocity distribution, the authors actually provided these three equations of conservation of mass, momentum, and energy. And there are two boundary conditions given. One is the Marangoni shear stress, and another one is the heat exchange between top surface and the surroundings. I didn't quite get how they derive these equations, because there is no specific assumptions in this paper. And they actually say when you consider convective heat fluid, the model will be really complicated. But if you don't, the model will be very inaccurate. Then they give these equations, and I'm not sure if they consider that or not. From the boundary condition, there is convective flow, but I'm not sure.
This is a survey article, so it's very, even though it's 100-some pages long, it's also very concise, and then they go through a lot of we'll go through this.
Okay. So somehow they got this temperature distribution. These two plots are from a directed energy deposition with laser process build of a superalloy powder. The paper says the peak load for the upper layers increases because conduction heat loss through the substrate decreases. That makes sense to me. Just the surface will, the peak load temperature will increase when the surface, when the part builds up. But I didn't get that from these plots. I don't see what's the peak load. So, but I feel the statement makes sense.
So if you look at the temperatures here, I think it's probably easiest to look at the 400 to 600 Kelvin band. And so, one, the background temperature is increasing everywhere. That's because basically thermal resistance from that top piece down to the base plate is increasing because the part got larger. So if you look at the isotopic layer, the part is going to stay hot longer. How do you do that? Maybe today, maybe Tuesday.
Even with increasing conductive heat radiation flow attribute compared.
Yeah, we'll talk about what the dominant temperatures are later, but yes. So you're right that now your surface area is increased, right? So you have more ability to convect heat away, but a higher, the majority of the heat transfer is going to be through conduction. So you created a more resistive conduction channel. You also increased the thermal mass, so you have more ability to store temperature.
So the peak temperature here means not the highest temperature location.
Well, the peak would be as well, but it's tough to see.
Okay.
Because we have a lot going on between 1600 degrees Kelvin and 2200 degrees Kelvin, and this plot doesn't really show that. It's just showing level sets.
Okay. Here are the two plots we got from those equations, including shows the temperature and velocity distribution. So it's clear that the non-uniform temperature distribution in this molten pool is to a surface tension gradient. So the melted material will tend to flow. This black arrows indicates the velocity, and the yellow lines on the right plot shows the direction. Then is the cooling rate. There are two important parameters that affect the solidification structure. G, which is temperature gradient, and R, which is solidification growth rate. These two parameters are actually affected by the shape of the fusion zone and the temperature field. With these two parameters, we have a ratio number which affects the morphology of the solidification structure, and GR, which is what we call cooling rates. It affects the scale of the structure. The two plots on the bottom shows the relationship between cooling rates, or the ratio, versus the layer number. It also say when you build up the part, the cooling rate will decrease, and also the ratio will decrease, which means your part will be non-uniform because of these differences between different layers. Then these are the non-dimensional numbers. I think Packard number and Marangoni number we have already learned that from class. And Fourier number is pretty, it's pretty straightforward. It represents the effective well, it's just straightforward. But the thermal strength parameters is the one I didn't get. The description is the effective common process and material properties on the susceptible of the components on the thermal distortion. I think this involves a lot of variables. So I didn't quite get that.
Who did this?
Oh, okay. Then heat input is straightforward. The last thing is the process stability. There are two instability introduced in this paper. The first one is Kelvin-Helmholtz hydrodynamic instability. This will occur when the Ri number is smaller than 0.25. This instability is actually caused by the different velocity between the surface of the liquid metal and the shielding gas. This will lead to this humping on the surface. There might be a lot of parameters affect this instability, but the one is fully understood is that it's related to a fast scanning speed. So when you scan fast enough and exceeds a critical number, it will cause this humping. Another instability is the capillary instability. Typically, when you deposit the material, it will show this like half cylindrical shape. But when you deposit it too fast, the scanning speed is too high, and the molten pool elongates and separates into small spherical balls to maintain the uniform capillary. Then you get the shape, the shape in the right picture. They gave an equation L/D larger than pi, then the instability will occur. The L is the length of the deposit material, and D is the diameter. Yeah, so that's all I have.
Thank you. Questions, comments? I know you're able to get some of this stuff. And there are some papers that the next paper we go through goes through just basically what's happening at the melt pool. Very, very more careful fashion. It's kind of a general overview of the dominant physics that are going on. Any kind of questions, things that maybe we haven't addressed yet that were confusing?
So I have one. So just curious, depending on the heat transfer model, like when the laser hits the point, and then you see the heat distribution of the sample. Do they do like these kind of printing in like different environments, like maybe like a inert environment, like to control the heat transfer rate to affect the last metallic component?
So are you asking, do they change like the environment in terms of how it affects convective?
Yeah, that. So if that's going to affect your final product, so does controlling that environment affect? Is there some parameter that they have like become control or like?
Yeah. So I guess in general, it's well known that having oxygen in the environment is a bad thing. Like it's known that welding for decades and decades. So they try and keep the pressure of oxygen down as much as possible. They can't completely eliminate it. I haven't seen anyone like do the experiment where they put different anecdotally, if they lose control of, if they have like a leak in their chamber, they lose control of the pressure reduction, all of them turns out completely oxidized. That ended up only having to work with Johnson Johnson, and they had a leak in their chamber that they didn't fix, and everything turned out terrible.
Right.
But I haven't seen a people where they change the pressure reduction. I guess where I've seen it is where they looked at powder reuse studies, and they intentionally changed the pressure reduction because they were worried about oxidation of the unused powder.
So that might depend on the nature of powder too, right? Because like different metals can oxidize.
Yeah.
Oxidize them in different dimensions.
Definitely, yeah. We definitely have, due to the rate of oxidation, we definitely have it.
A lot of those simulations and plots that they're showing, they take into account the fact that this isn't a solid piece of material, that it's actually like a fused powder. Is there any special considerations you need to take in a simulation environment to get good results like this, or is the assumption that it's a solid piece of material?
Yeah, so that's, I think the answer to your question is it's still being worked out in the field. There's this huge range in complexity of computational models for this process. And there's a few different approaches. I'll probably get to it today. Video from Morris Livermore National Labs, where they are essentially considering everything in terms of, they say, here are the physics, and they have every reasonable set of physics built into there, and then they show these incredibly detailed simulations that show everything from all the different modes. I think it would be best explained when I show the videos of that.
Okay.
But those take an incredibly long amount of time to compute. So if you want to run that simulation, they do really small domains, just in the order of around a millimeter in size, a millimeter cubed, and even smaller than that. It takes, I think, 4 to 700,000 CPU hours to compute. So it's not very, you have to have access to supercomputers like Morris Livermore National Labs does to really do that. And then there's, on the flip side, there's some simulation packages that they try and strip away as much of what they call irrelevant physics as possible, and those definitely do not include the idea that you have powder. And I'm going to get to that probably not until Tuesday, whether or not you have to consider, or do you have appreciable heat conduction into unfused powder or not? Is that part of the equation? And then they can strip away a lot of other things too. So when I was on a project, we were looking at how do you basically make this prediction as fast as possible. And we were able to predict entire temperature fields, entire parts on the order of just a few minutes, the whole build process. But that is much less accurate than what you would get from a very detailed model. There's a company called 3D Sim, who was just bought by Ansys, that uses fairly simple models, and they compute temperature profiles on the order of about half a day to a day. So that's about at the same speed at which you can build something. It's about half a day to a day. So it's getting close to what you call real-time computing, but they're simplifying the models considerably. So it's all about what you're trying to understand and what your computational resources are.
I have the temperature profile of a part that's being printed. I sort of have the idea that as the height level or as the height increases, the temperature profile is going to change. It's going to almost expand. How can I use that to print a better part? Like what controls can I change on an actual additive manufacturing process? Like probably the laser power and like where's
So laser power and scan speed. So the biggest, I think one of the biggest problems in terms of us as researchers with these processes right now is that these companies that I mentioned in Tuesday's lecture, like EOS and Contact Laser, all these companies, they've invested a lot of money in these processes, and now they're trying to make as much money as possible to put the plans right now. And so they do not tell you anything that's going on the inside. Anecdotally, I've heard that they change the laser power as you go from layer, and clear to me by what basis they're doing that, but it's just known that there's power to the other questions, comments? All right, thank you very much. Okay, so this is revisiting a slide we went through on Tuesday. I just wanted to go back to this before we start going forward again, because it talked a little bit about some of the features I think will show up nicely in the videos we're about to see on this. And just a reminder, some ideas about in terms of temperatures that we're operating at. So laser powder bed fusion for metals. The background temperature, the environmental temperature, is in the order of somewhere around 20, which is, this is Celsius, this is essentially room temperature in a cold room, right? All the way up to about 200. And from experience that these systems, at least the way they're built right now, they max out about 200 C is what the chamber can get in terms of how well they're insulated and what type of heating elements they have in these. And then if you go and you buy an E-beam system, it's a much higher background temperature, given the area of 600 to 1,000. The other thing that's very different between these is the rate at which you can scan these lasers or an E-beam, and it's a very different range. So a laser, you max out somewhere around 2 meters per second. That's really pushing it in terms of how fast you can scan a laser. And then with the E-beam systems, you get all the way up to around 15 meters per second. And with these types of processes. And so this directly affects what type of parts you get and the way things are built. These are all slides I went through on Tuesday as well. Just a reminder, we talked about the anatomy of the part. Basically, in a laser powder bed process, you have your part right here, and then you have a support structure, and then below this is the build platform. This build platform is what's fixed into the machine. So here's where you'd have basically bolted in here, 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 and then somewhere down here that's off the screen. Okay, and then we finished Tuesday's class. The very last thing we talked about is that actually we didn't quite get to this, but then there was a question of laser scan profiles, right, and how that affects things. So what I'm showing here, I mean, this slide and the next slide are just two examples, but one, just to make sure it's clear, if it wasn't clear already, is that you are building this part in a layer-by-layer fashion. I hope that's clear to everyone by now. Basically, here would be your build platform down here. And then every layer you build up, layer by layer by layer. Okay. And then within a certain layer, you have a certain scan profile. So here is 2 consecutive layers. Here is, they're just showing these side by side, but here are all your parts that could be potentially in a build platform. This is from the Air Force Research Labs. Dr. Graber was an Air Force person who now will be starting at Ohio, actually he just started at Ohio State as a faculty member in industrial engineering a few weeks ago. So if any of you are still looking for like a research advisor who does additive manufacturing, he's brand new in the department and he has a lot of experience in these types of processes in the industrial engineering department. But what this is showing here, it's really tough to see, but this is time. Okay, so this is not a heat map or anything. This is time. And so this shows at what time the laser hits a certain part. And so the blues would be at the very beginning of a part build, and then the reds, purples are going to be towards the end. It's not really too important, but what they did here is they wanted to understand if you put something very, very late in time in a space where you're not expecting, how is that going to affect the properties? So you can see this kind of changes from the blues to reds here, then all of a sudden it flips to red in this part. And they were looking at certain properties of the part. That's kind of besides the point. What I wanted to show here is that this was using a kind of like a stripe-like raster pattern. So the raster would be going back and forth here along this stripe. This is, again, time, so it starts on this end, goes all the way through. And then what you notice here, I guess I'll ask maybe, what do you notice about the stripe patterns from layer to layer? Yep, you did it with your hands. So it's rotated. And so I don't know about all machines, but say if you buy an EOS machine, it rotates 67 degrees at each layer, actually. So the reason for this, basically that means not perfectly, but approximately every 6 layers, it then gets back to where it was, but it doesn't quite, right? So it's actually, it takes a lot of layers before you get a repeat in the pattern. Okay, and so what that does is we get into discussions of residual stress, thermal loads, et cetera. What that does is that on average, it kind of averages out the thermal load and residual stress that an individual part sees if you rotate the scan pattern in each layer. So that's one thing I want to point out then. You have this rotation, right? So the scan patterns are generally in this direction on this layer, generally in this direction on this layer, and then if we were to go to the next layer, that would then rotate again. So that's just a kind of I would say an ad hoc strategy that people in the field have learned over the years to do in terms of influencing the quality of what you make. So that's I guess one thing I wanted to show here. The next one is that there are even more sophisticated scan patterns that people have looked at. These are the island type scan patterns, and what they're doing, say if they have some sort of rectangular cross section, they would say scan here in this quadrant here, and then they would jump in a random fashion here, and then say here. I'm making up what you would do, but basically they're jumping around where they're actually applying laser energy in the hopes that they can try and help diffuse and put a more uniform thermal load on that part, as opposed to having one side that's really hot and one side that's really cold. So these are just other strategies that people have developed. And then, like I was talking just a little bit ago about how companies trying to make as much money before the patents run out, all this is completely locked down in patent. So if you see, look at EOS, it's more of a scan strategy like this, and then Concept Laser and 3D Systems use more scan strategy like this, and so they even patent what their scan strategy is, and to lock other competitors out of that environment. So it's not all engineering, it's a lot of other things in terms of legal issues and things that the people are, that make maybe working in this space a little bit difficult, but also the companies are trying to make money, right? And these machines wouldn't exist if someone wasn't making money off it, right? So, but anyhow, there's a lot that goes into this. This is kind of beyond the scope of this class in terms of these kind of ad hoc little fixes that people come up with. But it's just, I think it's good to know in terms of when you see the videos, you want to understand kind of why they're doing some of the things they're doing. I think this helps. All right, so I'm just going to play a few videos. This will look a lot like other things you've seen before. just so I think it may help to kind of see the complexity of these scans and things like that. And I'm going to go through this for metal laser, polymer laser, and metal electron beam to kind of show some of the differences that you may see here. So, unfortunately, this whole system doesn't work with sound, but I don't think we really need to have sound on this. I'll just kind of talk over it. DMLS, this is the brand name that EOS uses, so but this is still laser powder bed fusion. So you can see kind of like the stripe pattern that we saw on the first one that was looking at this 67-degree rotation at every layer. You see this kind of goes in a stripe-like pattern. The back and forth of this raster is so fast you can barely see it. It almost looks like there's a line source, but that's really the laser scanning back and forth. So this is making two kind of like a nullus type structures. This is the recoding of this, and if you look, you see that the stripes have rotated, right? Just like that image before showed. Okay. It's not too obvious here, but there is smoke that comes off this as well. It's basically vaporized metal and soot. It comes from this. You can't really see it, but it's tough to see in this video. If you were to see the actual process live, you can actually see it a little better. Yes.
So is this similar process to what you were showing before, where it's kind of bars for the rasters going 90 degrees to the bar, and the bar skating across?
Exactly. So just say, for instance, these are these kind of tracks or bars, and what's going on is that this laser is going back and forth really fast. So it's going back and forth so fast that it looks like a line moving, actually. Okay, so that was laser powder bed fusion of metals. Here is this is another one with metals, just because this one more clearly shows that laser raster path. This is a process, this is at Carnegie Mellon. And the reason why I like this video, it's obviously it's a little bit more poorly shot. It looks like someone's just holding up their cell phone camera. But this shows it in a little bit slower speed, so you get a better sense of what's going on. But it looks, so you can kind of see how the laser is going really fast back and forth, even though it looks like a line source, it's actually rastering back and forth really quick. But this kind of nicely shows these bands that are going side by side. So you also see sparks flying off, right? So that creates basically those either vaporize or they remain as little small parts of metal that will could cause problems. You also may have noticed that at the very end, it very quickly circumscribed the entire part. Maybe I'll go back. Okay, let me replay that again. Let's see if I can. Okay, so just watch quickly be very fast, right? So the laser moves incredibly fast, but it is going and circumscribing the entire part to give a fairly nice, what it's trying to do is improve the surface finish at each layer, because that's what's you're going to ultimately see. Everything in the middle, you're not going to see once you build this up. If you have a nice surface finish, it does that last little move. Almost faster you can see it happen. Yes, AJ?
It almost seemed like there was a difference in height between the fused powder and the unfused powder. Is that something that is considered in these processes?
Yep, exactly. So no, good observation. So so the powder is, you can only pack powder at a certain density, right? So if you have purely spherical particles, which you don't have, I believe the theoretical limit is 67%, because it's basically how, I can't draw it here, but if you have perfectly spherical powder, the most dense you can pack it is in this arrangement, right? You're always going to have porosity in between. Now, if you have not perfectly spherical particles and you have a distribution of particle sizes, you actually can get the higher densities because you can start to put smaller ones in here, right? But really, you're talking about somewhere maybe 70% packing density, right? So now you take this powder, which has basically air in between, so it's creating more volume than the metal itself, and then you're melting it, and that melting process is going to essentially get rid of most of the air. And so then you're right, you get then a densification of this. And so from previous discussions, powder is on the range of, say, somewhere between 30 and 50 microns, but usually the layer heights that you use are 30 microns or less. So what they do is at every layer, they fuse the metal, it shrinks then, right? So you basically, whatever the powder height was, it was somewhere around 50 microns, is now going to shrink around somewhere around 20 microns. But when they pass the recorder blade above, that's going to essentially fill in that gap at every layer because you can put powder on top of that. Does that make sense? Okay. This is polymers. I don't know why the video is so choppy. Hopefully this stops being choppy. Some of these videos are very tutorial nature, so they go through kind of all these things that we've already talked about. We'll get to videos in a second. All right, here we go. Okay, so as we discussed in that one table, the main difference here is that you don't have to use support structures with powder bed fusion for polymers. And that's because your temperature gradients aren't that high. So it doesn't require all that much temperature to melt a polymer. Let me go back just a little bit. Let's see, find it. Okay, and then the other thing I want to show you here is you get this very characteristic kind of spark from the metal processes. Here you basically don't even see anything. You see it just kind of darken, where it's going from powdered polymer to fused polymer. But there's not like this incredible like violent event of a spark happening. That's because, of course, polymers are very different than metals, but also the laser intensities are just not that high in comparison. This is showing after parts made. The other thing, because the temperature gradients are so small, you can make some pretty large parts in the polymer processes because you don't have to worry about basically thermal stress generating from large temperature gradients. So you saw the part he was holding was like this big. That's very difficult to do in the metals processes, actually, to get a part that big. Oops, before the ends. The other thing I want to point out here is towards the end. So the part support is actually the part is supported by the powder itself, and then when you're all done, just like the metals process as well, you have to go then retrieve your part from this pack of powder. So this is a technician kind of with a brush, just brushing away a loose powder from these parts. So you basically have this bed of powder, you essentially reach your hands in there. They have all these setups with vacuums that'll vacuum up the powder for you, but then you go and get your parts out of the build. Okay, E-beam. Okay, so this you'll see is very different here. What's going on, I don't know why the video is so choppy. Let me, okay, get rid of this. Okay, so they're not actually building a part right now. What they're doing is actually they're doing a background heat of everything. And so what they're doing is they're scanning. It's crazy, right? It's like some sort of EDM concert thing. All right, so what you saw at the very beginning was essentially this background heating. And so they're scanning, because they can scan the laser or the E-beam so fast, they're actually background heating everything. They're very lightly sintering that top surface, and they're keeping everything really hot. Here, before we saw kind of like little stripes, now you see like the whole field is lit up, right? And they're just scanning this E-beam incredibly quickly. They're just gonna, let me replay that again from the beginning, because I think it's interesting. Again, this is the preheat with E-beam. This is an independent source. It's just moving so fast it looks like you have these gigantic lines. There's this crazy pattern here. And then you'll see a final fuse going on with the E-beam process. That looks like you're somehow able to create a line of heat, but it's really just moving really, really fast. Okay, so the residual stress you can get with the E-beam processes are much lower because you can move the heat source so quickly, so you can actually even out loads more effectively. Okay, so I also thought it may be interesting to kind of go through what does the support around this machine. We've only really talked about what goes on in the machine itself, but there's a lot that goes on if you ever want to, put one of these in your garage. I wouldn't recommend it because it requires a lot to do this. But basically, they're pretty high-powered devices. They have cooling systems. They have recirculating units for air. They have separators. Basically, one of the issues with any metal powder, what happens to metal powder when it's airborne and you have some sort of heat source? Anyone have an idea?
Besides oxidation,
Besides oxidation, yeah.
there's some water.
That
It gets everywhere in the air.
it gets everyone in the air. And have you ever seen? It's a good example. Have you ever heard of a industrial bakery blowing up?
I mean, if it's titanium powder, that'd be a huge problem.
It's a huge problem. Yeah. So powdered anything is extremely flammable, and that's because their surface area to volume ratio is so high. So you get, basically you can light things on fire very, very quickly anytime you have powder in the air. And so there's a lot that goes into, especially as Nate mentioned with titanium. Titanium is an extremely flammable material, and so when the powder comes in, they basically don't let it get exposed to air at all. They try and keep it in the packed powder state as best possible. They don't let it go airborne and then have a bunch of powder in the air. That causes, it's essentially a bomb inside your little machine. All right, so these are fairly dangerous machines. They have, of course, then flammable storages. They have wet separators to make sure you can separate things appropriately. This is a powder removal station. So you would take your entire bed of powder and you would put it in this station, and then this is a glove box. Have anyone seen a glove box in a chemical lab before? But basically, you work everything through these gloves, and so they can keep the environment, say in an argon environment, which is pretty inert, or something that's safe, so they can actually, where you saw with the polymer case, there was just a guy or a woman, I don't know, I forget what it was, with their hands, and they're just taking the powder off the part. That would never happen with the metals processes because of a variety of different safety issues. And so they have these separating units. I don't know exactly what goes into this, but it's a lot. So these systems are pretty expensive for the system itself, plus everything that goes along with it. Hey.
So for an E-beam machine in which all of that surrounding powder is lightly sintered to the part itself, do you need to like get a hammer and like knock it off?
Basically, yeah. Yeah, break it off, yeah.
So it's like the powder separator is like this like shaker machine or something?
We'd have to go take out to CDME to look at their machine and see what they do. But yeah.
I'm wondering how you'd be able to do that without damaging the part itself.
That'd be
It would have to be so violent.
a big worry, yeah. So I don't know too much about E-beam, but yeah, I imagine that'd be an issue. What was that else? I was going to say some more, one thing else in this.
It's escaping me. Oh, yeah, yeah. So then the other thing too, this is the EOS machine. If you look at what 3D Systems does, they don't, uh, they basically have this nice system where the system is never exposed to air at all. So I don't have an image of this, but basically there's a cart that just rolls underneath here. And then in that cart is basically a completely self-contained system where they never let air ever enter it. It's always under an argon environment. So it's almost like this cartridge they bring in. Everything is inside the cartridge. All their canisters are fed in without all air interlocks. And the reason they have to do that is because 3D Systems is trying to make their name by having smaller particle sizes than everyone else. So you get finer, better, basically surface characteristics than everyone else. And with that comes that increased chance of causing explosions. So they have even more safety systems that are involved. They also do other things, like they have, instead of just putting this recoater blade, they're actually compact the powder layer at every layer as well to get higher densities, lower porosity. They're trying to create the best quality parts possible, and that, of course, boosts expense. Yes?
So are industries like willing to accept these safety over the advantages like assembly line? Because that's very streamlined and very safe by their standards, right?
Some companies are, yeah. And GE has invested a lot in this, so yeah. Yeah, it's expensive. All this.
Because like they're very picky about anything that like compromises safety.
Yeah, well, that's why they have all
This
these.
one seems to like have a lot of limitations compared to like a traditional assembly line.
I mean, that's why they have these basically engineering controls on it. I wouldn't call casting the most safe thing either. If you look at what goes on there, they have a bunch of usually men just around with little crucibles of metal. They're pouring it in, so that's not safe either. I think there are a lot of dangers everywhere, but yeah, there's definitely some dangers associated with this process. Okay. All right, here's the video I said I was going to get to. Okay, so that was kind of all the infrastructure and everything that's going on in terms of what is PDBF. That's what all these slides were about. Switching content a little bit, this is now observations of the process. So we looked at these videos, and they were just videos that are made for YouTube, and people can look at it and say ooh and ah. We'll go through a few examples from more technical literature so we can start to understand a little bit better what's going on in this process from more of a physics and at the more the microscopic or systems level of what's going on. So what you're seeing here, this is going to be high-speed video from the laser spot. So just this is a static image right now. You can see the laser spot, and here's all your bed of powder. Kind of orientation, this is, I don't know which one's X and Y because I didn't do the experiment, but I do know that Z is out of the page. Okay. And why am I not getting video to show up here? No, it was working on the YouTube video, so I'm not sure. Okay. Everyone can see that? Okay, we'll watch this a few different times because I want everyone to walk through and kind of see if they're observing the same things that I observe having watched. I probably watched this video 30 times by now. It's a lot of fun. So okay. Keep annotations. Not sure that's not working. All right, let me. Cannot play media. That's always fun. So now the problem is I have to try and figure out where I first ever saved that video, which is not going to be fun. Okay, that's annoying. I don't know. I don't know what to say. Okay, sorry about that. I will, yeah, this is one of the cooler videos you'll find on Autodesk Fusion. So I will hunt down this and email it all to you because I think it's important to see. Okay. Basically, what you saw before in the other videos is this line that's going so fast you have no idea what's going on, right? And it's tough to decipher. So this is nice because they're using an extremely high-speed camera. This is having purchased high-speed cameras before. I'm guessing this camera cost somewhere around $150,000. So it's a very expensive camera. Of course, it's not going to work. So trying to understand what's going on at this level. Trying to understand the physics. So what you'll see is some things that you probably have observed from simulations before and also from your homework assignment, that the melt pool, basically this really hot area, trails the laser. We saw this with looking at the Rosenthal paper and some of the homework you did. What you also see is there's going to be vortices in this melt pool. So basically you start to see kind of metal flowing in this region as this goes along. You'll see occasionally, you'll see that you get these ejections of molten metal, what they call spatter, out of the melt pool. Okay, so we'll discuss why that happens, but basically imagine a laser hits this and now you see these little ejections going on out of this melt pool. And then what you'll also see is that this melt pool also has an attractive effect where you see powder migrate into the melt pool as well. So it won't necessarily be that, I mean, obviously it doesn't have like this Jedi-like force, right? But there's something that's causing the adjacent powder particles to be drawn into this melt pool and either completely melt themselves, even though they weren't hit by the laser, or partially fuse. Okay, and that they'll start to be, creates this kind of rough surface on the outside here as well. So sorry there's not a working video on this, but we'll try and get that fixed. These videos should work because they're in the folder, I would think. Okay. I know where to find these ones. This is much better. Other observations, this is pretty recent work, 2017, but then they've had some cooler videos that I asked for them. They said not until we publish it because they played this in Texas when I went to that conference of even better videos than this. But what they're doing is this really interesting experiment. And this is an experiment that you couldn't do, you can only do this experiment a few places in the world actually, because you have to basically have to have a synchrotron or X-ray source, a very precise X-ray source to do this experiment. But what they're doing is they're not using a commercial system, they're creating this really, really tiny powder bed fusion system here. So this is this little tiny powder bed fusion system because they want to understand what's going on when the laser hits powdered metal. And they're creating a block of material and they're just putting a thin layer of powdered metal on top and they're hitting it with a laser for basically microseconds and trying to understand what's going on. The same time that they're doing this experiment, you can see they have this is in meters here. So this is 0 meters, 38 meters, that's pretty long distance, right? It's about 1/3 of a football field about, right? A little more than that. And then they have an X-ray detector on this side. So if it's X-ray, they're shooting a synchrotron X-ray into this. They have this little shutter. You actually see the shutter open and close in the video. And so they're looking at inside of the melt pool what's happening. Because we usually don't have access to that information. But if you use X-rays, you can see inside things, right? So this video is not going to play in PowerPoint for some reason, but we can, I know exactly where this one is. So keep annotations. Okay, so for some reason you guys cannot see that right now. There we go. Okay, we'll replay this a few different times. What you're going to see is you're going to see the shutter opening. Okay, let me pause that for a second. How do I pause? Oh, there we go. Okay, so to orient you to what's going on. So you see the shutter opened. So it allows X-rays to hit What this is below, this is solid metal in this region right here. Okay. Above it, then they put just a little bit of powder on top, and then in a little bit, you're going to see a laser hit the surface, and we're going to watch what happens. So laser, this is waiting. In the bottom right, once it goes to 0 seconds, the laser has started. So you can't actually see the laser in X-ray, but we'll see the effects. But you saw that some of the powder is moving around. Okay, so this is melting of this powder. You can see the melts forming here. You also see like this confetti effect, right? The powder is flying into the air at this laser spot right here. Also note, this is a 340 watts of, the laser power here is 340 watts. We'll watch a different video in a second, which is going to be higher power. Okay, so then we see the melt pool kind of undulating as the laser turned off. Sorry, you have to watch this bottom right. This is the time in which the laser is on. Now it turned off. So you see this molten laser, this molten melt pool is kind of undulating, moving around, but now it's going to solidify. Laser off, powder still going in the air. But just keep in mind the length of time that this was taken. This is 1,000 microseconds, right? So it's not like the powder just stays in the air. That's just how long the video is. It's still in the air. Okay. So very, very expensive experiment. Very cool experiment. This is cool work. The people who published this, they pretty much made a whole journal article off of that, and I saw the NSF award that this came from, and these videos cost like, I don't know, probably $100,000 a piece to acquire in terms of research funds. All right, so previous video was 340 watt laser. This is going to be 520 watt laser. Okay, so this is going to be higher, essentially, energy density put into the system. You'll see the same basic thing happen, but then I want kind of hear what you find and see the differences between the two videos and two different laser powers. Same idea, waiting, laser on. Okay, melt pool is forming. Laser still on. Okay, laser off. Okay, so what's different? Yep, so the depth of the pool was deeper, right? At the very end,
You get like this trapped region of molten metal beneath the surface.
yeah. So the question is, yeah, is that molten metal or is that air?
Air?
Air. So here's molten metal, that's air. So in this case, it drove the melt pool really, really deep, and then what remained is a pocket of air at the end. Okay. So we'll watch this again just so everyone can see it again. Shutter opens. All right, laser's about to hit. Kind of a violent event. Powder flies everywhere. Melt pool goes deeper, right? So you can see it kind of this, almost like this finger pushing into the metal. Laser turns off, and then a pore remains. Okay. Yes.
Is there no modulation at the end?
Sorry.
At the end, the pools and cavities left.
Okay. I didn't. I guess I have to watch again. That's maybe a good point. We'll watch again.
Is it in the same time scale?
It's, I believe it's the times. Yeah, both 1,000 microseconds for the laser. Yeah, maybe it settles down a little bit. You do see a considerable amount of, we'll say, undulation in the melt pool while the laser's on. So you see basically this being forced really deep, and then at the edges, you see these kind of plumes coming off on both sides. So in both cases, you have a lot going on in terms of what's happening at the melt pool. It's kind of flying everywhere. Right? But yeah, but also this deeper melt pool, pore formed. Okay. All right, so with that, we're out of time for today. We'll get into all that fun stuff on Tuesday. I'll find that video and send it to everyone of the high-speed camera from the top surface so you can see what's going on there. That one's a fun video as well. So, All right, have a nice weekend.